In this lecture, we will continue with the Redfield equations and talk about rotating frame relaxation. That is, what happens to relaxation when we turn on a radio frequency field in addition to our B0 field. And then we'll finally address the question of what happens when the fast limit, Redfield limit, isn't achieved, when we have slow processes. So frequently, in fact, when analyzing pulse sequences, we ignore relaxation during a pulse. As you start to make calculations of relaxation rate constants, you see for the size molecules that you're working on, the relaxation rate constants, the T2s, are likely to be milliseconds, and hard pulses are typically 100 microseconds or shorter. So to a good approximation, one frequently can ignore relaxation during a pulse. On the other hand, relaxation can be important if we have extended pulse trains or selective pulses, Toxie experiments where you might have the Toxie field on for 40, 70 milliseconds, and then the R1 row experiment. And much of what we'll talk about the rest of today will be the R1 row experiment because that's becoming increasingly powerful for application to biological macromolecules. So just to remind you about the rotating frame of reference and RF fields, we'll review briefly the terminology that we'll use throughout this lecture. So of course we have the B0 field, and then we have the B1 field, the RF field. The B1 field is in the transverse plane with some amplitude B1 and a phase angle phi. And then we have an effective B field that is the vector sum of the two. And I've already written this in the rotating frame, so delta B0 refers to the reduced static field in the rotating frame. So the reduced static field, of course, is related to the resonance offset as shown by the first equation. The resonance offset, capital omega, is the Larmor frequency omega naught minus the frequency of the RF field. The tilt angle is given by geometry as the tangent of the tilt angle, either B1 over delta B0, or we can think in frequency units, omega 1 over the offset, and that will usually be what we use. And then the effective field is the vector sum of the two fields, and again we can think of that in terms of either a B field or an effective nutation frequency, omega effective, and most of the time I'll use omega effective, and sometimes I'll just call it omega E rather than effective. But in either case, we just have the vector sum. Now back in the laboratory frame, before we switch to the rotating frame, of course the B1 field is circularly polarized, or at least the part that is effective in causing rotations of the magnetization is circularly polarized in the proper direction, and there's a counter-rotating field that we'll ignore. So our laboratory frame Hamiltonian now has the Larmor frequency, fluctuations along the Z field. We're only going to talk right now about adiabatic fluctuations again. But now we have the circularly polarized B1 field with an amplitude omega 1 and frequency omega RF. You'll recall when we did either the random phase model or the Redfield equations that our first step was to transform into an interaction frame in which only the fluctuating fields appeared. So we want to do the same thing here. We want to transform to a frame where we only have delta omega Z appearing in the equations. And it's easiest to do that transformation in steps rather than writing down one transformation operator. So we'll do this in steps. The first step is going to go into the rotating frame. And this, of course, you're familiar with. If we transform into the rotating frame and assume for convenience that we have an x-phase RF pulse, in the rotating frame, rotating at a frequency omega RF, now the B1 field looks time independent and it's on the x-axis. We also then replace omega naught with the offset frequency, capital omega. So this you're very familiar with. Notice this is different than where we started with the random phase model. In the random phase model, we switched into a frame that was rotating at the Larmor frequency omega naught. Here we start by switching into a rotating frame that's rotating in omega RF so that we remove the time dependence of the B1 field. The next step is to transform into a tilted frame of reference with z-axis pointing along the effective field. And I'll indicate, at least for a while, that second frame by primes. So for example, if the RF field has x phase, then in the laboratory frame, an IZ operator projects into the tilted frame with projections along the IZ prime axis and along the IX prime axis. And similarly, an IX operator in the laboratory frame has its own projections into the new frame of reference along the IZ prime axis and the IX prime axis. So I can use these new projections to see what the Hamiltonian looks like in the new frame of reference by replacing IZ and IX with their projections into the new reference frame. So that's done here. And then I start collecting up like terms. So now I've collected up all the terms other than delta omega z in one bracket, and then the other term is the terms that are proportional to delta omega z. And now I have to remember what I mean by omega e. Omega e is the square root of the vector sum of the offset and the omega 1 field. So that first term is simply omega e squared over omega e. And now the second term is the fluctuations projected onto the tilted frame. I started out just caring about the projections along the z-axis. Now I've projected them onto my new tilted frame. I can now write this as omega e times the operator IZ prime, the z-axis operator in the new frame, and then h1 projected into the frame. And I can either do that as shown using IZ and IX, or I can replace IX with I plus and I minus. And you know that I'm going to do that so that eventually I have spherical tensor operators. Having done this, we can cast things back into our red field picture, in which we have the fluctuating Hamiltonian expressed in terms of the stochastic functions f and then the spherical tensors b. In this particular case, we only need the rank 1 spherical tensors, so I've written them here. And again, they have normalization factors that we just have to take care of. And now we can do the transformation into the interaction frame. The last transformation transforms that Hamiltonian into the interaction frame. The omega e IZ prime part disappears. But notice one important difference now. The complex phase factor is e to the IQ omega e times t. So this phase factor depends on the omega E field, not simply the eigenfrequencies in the laboratory frame. We have the contribution now from the B1 field that we turned on. Otherwise, this looks more or less like our normal sort of expansion. And we can go on and plug this into the Redfield equations. There's one subtlety that won't be necessary now, but could be necessary in more complicated problems. And that is, once we turn on the B1 field, we might be making some operators secular when they were non-secular in the laboratory frame. And in that case, we might want to redefine the operator basis to lump together all the operators that are secular with respect to each other. In our problem, we won't need to do that, but it's just something to keep in mind. So the relaxation rate constant for magnetization that's locked along the IZ prime axis is called R1 rho. And we would get it then from our usual Redfield type expression where we have double commutators summed over the basis operators and taking the trace, etc. And when I work out all those operators, I simply find that R1 rho is equal to 2J at a frequency omega E. So again, the frequency that comes out is the frequency of the effective field, not the laboratory frame eigenfrequencies. And remember that J comes from the fluctuating fields. We have now this term sine squared theta. That again came from projecting the fluctuations onto our new z-axis. If the autocorrelation function decays as a single exponential with rate constant k, once again I can just integrate that expression, and the result of doing the integral is shown here. So R1 rho for the two-state hopping model, or actually this could be any number of states. We haven't specified that it's two states. But we have sine squared theta term that comes from the projection into the tilted frame. We have the variance again. But we have this new dependence. We have, in addition to dependence on k, or the correlation time 1 over k, we have a dependence on how strong the effective field is. And if we go to the two-state process, we remember that the variance of the two-state process is PA/PB delta omega squared. So here's a very famous result. This is the R1 rho contribution from two-site hops in the fast limit. And as shown, it depends on omega E squared. If omega E went to 0, we would be back to our normal expression. But as omega E gets larger, we can suppress the effect of the two-state jumps. If omega E approaches infinity, if we could turn the B1 field on a very strong level, the denominator becomes very large, and then R1 rho disappears. This, of course, is what makes R1 rho and spin locking experiments very powerful, is that we can control the amount of line broadening as we turn on the B1 field. And now remember that omega E was defined relative to the offset. I wasn't completely clear what I meant by offset when I'm jumping, but that's going to be the average resonance offset in the fast limit. Remember, in the fast limit, the line has collapsed to a single resonance at the average. So omega E here means the effective field that's the vector sum of the average resonance position and the omega E field. And that turns out to be very important in what comes next. And that's, of course, a consequence of being in the Redfield limit. The Redfield limit said we had a single line collapse to the average frequency. Okay, so we're going to leave the Redfield equation behind for a while now and finally start to ask what happens outside of the fast limit. So just to remember, when we were looking at the random phase model, we included some of the higher order terms and in the Taylor series expansion, and this led to the conclusion that the Redfield or fast limit approximation required that the standard deviation in the fluctuations times the correlation time be much smaller than 1. In terms of Hamiltonians, that means roughly that the width of the Hamiltonian, the width of the coupling, times tau c is much less than 1. When this assumption is violated, unfortunately, we can't fix the problem simply by adding a few more terms into the Taylor series expansion. Once this assumption is violated, the Taylor series expansion converges very, very slowly, so we would have to add an impractical number of terms to keep using that approach. So we need to switch to some other approach. And in solution, this is primarily leads to what's called chemical exchange effects in NMR. There are roughly two more or less parallel approaches that we'll talk about. We'll start by talking about what are called the Bloch-McConnell equations, and then finish by a brief discussion of a generalization of the Bloch-McConnell equations called the stochastic Liouville equations. And again, we'll be thinking mostly about chemical kinetic processes or conformational processes. And if these are happening on a microsecond or millisecond time scale, then we could easily be outside of the Redfield limit in practice. So now we can imagine a chemical reaction. We're going to take a couple of slide break from NMR and just talk about chemical kinetics. Here's a chemical reaction. A plus C goes to B plus D with forward rate constant and reverse rate constant. Now, we can't split nuclear spins into pieces. So that means that any spin we're monitoring is in one of the reactants and then ends up in one of the products. It can't split up and end up in two of the products at the same time. And that's a tremendous simplification in our experiments. It's also the case in solution. If we leave aside some fast mixing or laser jump experiments, most of the experiments one does in solution are at equilibrium. So the system may be fluctuating, but it's at overall chemical equilibrium. And with these two assumptions, if the spin of interest is in reactant A and product B, then we can reduce the equations using pseudo-kinetic rate constants because the concentrations of C and D are constant at equilibrium. So now K12 prime is K12 times C and K21 prime is K21 times D, and the system looks two-state-like. So this is very handy. A large number of seem like complicated problems reduced to our old friend, the two-state process. And then we can write down a kinetic rate equation. Again, this is chemical kinetics. We just have gains and losses. I don't want to write primes all the time, so I'm dropping the primes, and we just have to remember that these sometimes might be pseudo first-order reactions. But there's the chemical kinetic expression. And again, we'll just remind ourselves that the eigenvalues of the rate matrix are 0 and the sum of the two rate constants. So once again, the only time constant in the problem will be 1 over KEX. So we know the Bloch equations. The Bloch-McConnell equations are named after Harden-McConnell. And these simply add in to the Bloch equations the effect of the chemical jumps or conformational jumps. So here are the Bloch-McConnell equations for two-state jumps for Z magnetization. So Z magnetization in the block equations would just relax with R1 back to Boltzmann equilibrium. But now, in the presence of states A and B, magnetization can be transferred from A to B and from B to A when the molecule changes state from A to B and carries the nuclear spin along with it. And this is basically all there is to say about longitudinal relaxation for two-site processes. All we have to do is solve this differential equation, which of course is quite easy to do in Mathematica or other programs. And frequently, these equations will be written as deviations from Boltzmann equilibrium, again, just for simplicity. And of course, now the Boltzmann equilibrium magnetization is distributed amongst the different sites depending on their relative populations, as shown here. So we can write this in compact notation in which the bold-faced symbols are now matrices, so delta MZ becomes a column matrix, and boldface R is now the Bloch-McConnell matrix, including both R1 and chemical kinetics. Frequently, the superscript 0 is used to indicate the relaxation rate constant in the absence of any chemical exchange process. So R1 super 0 there would mean the relaxation rate constant coming from overall tumbling, dipole-dipole interactions, the chemical shift anisotropy, quadrupole relaxation, etc. And then we have the contributions from the jumps. So these have the formal solution, of course, as the exponential of a matrix. And as we've seen before, the matrix terms can be written with transfer amplitudes A. In this particular case, they, of course, are given by the matrix elements of the complex exponential. And we could write those out explicitly. It's not worth really doing it. Mathematica will happily calculate those for us. So what do these equations mean? That's indicated here. So I picked a population of 1/3 for state B, 2/3 for state A, gave both spins the same R1, and now we can simulate what happens if I invert the Z magnetization for spin 1. And if there's no chemical kinetics, we just get inversion recovery. The black curve just shows recovery of spin 1's magnetization back to equilibrium. But now, if we have chemical exchange with a rate constant of 10 per second, now we can say green is the recovery for spin A after inversion, and the red shows the behavior for spin B. Spin B now is perturbed away from Boltzmann equilibrium and then eventually recovers back to Boltzmann equilibrium. So this is population transfer. Z magnetization is populations of the eigenstates. We're transferring population from one spin to the other due to the chemical exchange process. For transverse magnetization, the Bloch equations look very similar, except of course now we have chemical shift precession in the two states because we have transverse magnetization. So I've written the equations here for M plus. I could have written them for M minus as well. The equations would look basically the same. We can solve these in a similar manner as for the longitudinal equations. We would have an exponential of the rate matrix, and then we would ask Mathematica to solve the rate matrix for us. So we, of course, can calculate the time course of the magnetization by forming the exponential, just as for the longitudinal equations. On the other hand, frequently one is interested in what the frequency spectrum looks like. And it's somewhat inefficient to calculate the time dependence of the signal just to Fourier transform it to the frequency domain. So just as way of completeness, we'll briefly indicate how we would more directly calculate the frequency spectrum. So again, we'll use the shorthand of having the boldface terms indicate matrices. So we have column matrices and then the Bloch-McConnell matrix, in this case for transverse magnetization. Now we're all familiar in NMR with the Fourier transform, but there's also a transformation called the Laplace transform, and its definition is shown here. And the Laplace transform has the convenient property that the Laplace transform of the derivative of a function is very simple. It's s times the Laplace transform of the function itself minus the initial value of the function. And we can use that property to great use here. So we start with our differential equation and take the Laplace transform of both sides. And because of the derivative property now, we have an algebraic equation. We no longer have a differential equation. And we can simply solve this equation for m plus of s. So we collect terms up on each side, and we have a solution for m plus, now in the Laplace domain. And then there's a simple trick, and we'll get to that simple trick in a moment, because first of all I have to remind you that S has to be understood to be a diagonal matrix. In this case, it's not a scalar quantity. So the trick is to replace S by I times omega on both sides of the equation, and then say that our complex spectrum, our Fourier spectrum, is then obtained by just adding up the columns of this matrix. So I've introduced a row vector just to sum the columns of m plus, and if I substitute in the populations, we have this compact expression then that directly gives the frequency spectrum. So we just have to calculate the inverse of the quantity in parentheses rather than having to calculate Fourier transforms, etc. So here are some numerical calculations. Again, I chose a population of 1/3 for site B. And here's the spectrum with no exchange. I set the frequency of site A to be 0, and then the frequency of site B was set to be 100 radians per second. And now we turn on some exchange broadening. Right now we're in what would be called the slow exchange limit. Delta omega is 100 and KEX is 2. Remember, our condition for being in the fast limit is that KEX would have to be much larger than delta omega. So this is the slow limit, well outside applicability of the Redfield equations. And you can see the first thing that happens is that the lines start to broaden. And now I can make the rate constant larger. Here the rate constant is matched to the frequency difference between the A and the B states. And the resonance lines have started to merge together, and we have a very broad signal. So this is called intermediate exchange or coalescence. And in practice, the peaks frequently just disappear from the NMR spectrum altogether. And one has to find new solution conditions in order to bring the peaks back. Now I make the kinetics faster, and a line starts to grow in at the population average position, and now we're starting to enter the Redfield limit. And if I make the rate larger, now KEX is about 10 times delta omega, and now you can see we have a Lorentzian looking line at the average resonance position, and as the rate gets faster and faster, that line will continue to get narrower and narrower. Remember, for 2 site jumps, our expression for the adiabatic rate constant was the populations times delta omega squared divided by KEX. So once we're in the Redfield limit, as Kex increases, the rate constant gets smaller, and therefore the line gets narrower. And that's what you see here in the simulation. So in many, but not all cases, it's approximately true that the overall rate constant is the sum of the rate constant from other processes, such as tumbling, plus the contribution from the jump process, here called Rex. In slow exchange, each line is broadened, and it's broadened basically by the rate constant for jumps out of that particular state. So the resonance for state A is broadened by K12, the jump rate from state 1 to state 2. And the resonance line for state B is broadened by K21, the rate constant for jumps from state B to state A. And then in fast exchange, we get the expression that we're used to, the adiabatic contribution to R2 from a two-state jump. So in slow exchange, the two lines are broadened basically by the loss terms, the jump rates out of that particular state. And in the fast limit, we have the single line and then our adiabatic expression. Now, remember, if the populations are skewed so that the B state has a lower population than the A state, then K21 will be larger than K12 just from chemical equilibria. And that means the resonance line for the B state is broadened more than the resonance line for the A state. But the B resonance line is already smaller because its integrated area is proportional to the population. So the minor state resonance is both weaker in intensity, but much broader potentially than the A state. And in many cases, particularly in biological macromolecules, the resonance line from the minor population states are completely invisible. They're broadened out. For example, if we had 5% of a second state in the slow limit, that line is going to be 20 times broader than the major line. And it's going to have an integrated intensity 1/20th of the major line. So this is a very short, fat peak, and you're never going to find it in the NMR spectrum. So that raises a problem that we'll have to address in the next lecture, which is that the mere observation of a single resonance for a spin doesn't tell us that we're actually in the fast limit for a chemical exchange process. We could be in the slow limit, and the other resonance signal is just invisible to us because it's too broad. So we'll need ways of addressing that problem. For right now, you can just remember that we have that issue. So this graph on the right-hand side just reproduces the kinds of calculations that I showed you on the previous slides, and just reminds you that the line width is proportional to R2, something that you all learned a long time ago. Now, this is almost all that I want to say about transverse relaxation under free precession conditions. There's not much more to it other than solving the Bloch-McConnell equations. In the slow exchange, we have some limiting result about how broad the lines are. In the fast exchange limit, we have the red field result. In the middle, it's mostly numerical calculations. There are some approximations for what happens in intermediate exchange, but the approximate equations are complicated enough that it's almost easier just to do a numerical simulation. But the last thing I want to say about free precession has to do with what happens if we have multiple quantum coherence. And sometimes this is presented as being complicated. But once again, the spins aren't very smart. They only know what happens to their frequencies. So a double quantum frequency, of course, is the sum of two frequencies. and the zero quantum frequency is the difference of two frequencies. So now, if the molecule is jumping from state A to state B, and we have double quantum coherence, we simply have a jump between the double quantum frequency in state A and the double quantum frequency in state B. So the frequency difference now is just the difference in the two double quantum frequencies. And similarly, the frequency difference for the zero quantum frequency is just the difference. So in an exchanging system, the difference in double quantum frequencies is easily calculated to be the sum of the frequency differences for the I spin and the S spin. And for zero quantum, we simply have the difference in the change in frequencies between the two. But otherwise, we can just take delta omega double quantum and put that into the Bloch-McConnell equations if we want to understand chemical exchange for double quantum coherence. If we want to understand chemical exchange for zero quantum coherence, we just take delta omega ZQ and put that into the Bloch-McConnell equations. There's nothing particularly special because, again, the spins just know what their frequencies are. They don't really know anything else. Now, the one interesting thing, though, of course, is that depending on the signs of delta omega I and delta omega S, the double quantum frequency might be large and the zero quantum frequency might be small, or vice versa. So it's possible that the double quantum frequency could be in the fast limit and the zero quantum frequencies could be in the slow limit, or vice versa. So you might be able to shift around which frequency range you're in by changing from single quantum measurements to double quantum measurements or zero quantum measurements. It also means that there's a kind of Troisi effect for multiple quantum signals when in the presence of chemical exchange, and that's shown here. Here I've picked some value of delta omega I, and now I'm varying delta omega S for the zero quantum and double quantum frequencies compared to single quantum. So single quantum relaxation of the I spin doesn't care what's happening to the S spin, but the double quantum and zero quantum terms, as you can see, depend on this difference between the change in frequency for the I spin and the S spin. And depending on those relative magnitudes, REX could vanish for either the double quantum frequency or the single quantum frequency. And there's occasional times when this can be useful or will suddenly cause resonances to appear that you hadn't seen before. So in BPTI, there's some triple quantum signal that is very strong, even though the single quantum signals and double quantum signals aren't observed. And it just so happens that the differences in the triple quantum frequencies happens to be very close to zero, so that line becomes sharp when the other lines are very broad. So that's just to say that there's nothing special about multiple quantum chemical exchange. It's all just about frequency jumps. So we already have seen that since transverse relaxation, or at least the adiabatic part of transverse relaxation, comes from fluctuations in precession frequencies, that we potentially can refocus the effect of those fluctuations if we can pulse fast enough. And this, of course, is the Carper Selmy boom Gill experiment. So we have a series of 180-degree pulses. One unit of the Carper Selmy boom Gill sequence is two 180-degree pulses, so two spin echoes arranged in this symmetrical way. So we have a delay tau CP, a 180-degree pulse, a delay 2 tau CP, another 180, and then a final tau CP. So one unit is 4 tau CP long, and the way the experiments are commonly done, tau CP is long compared to the length of the 180-degree pulses. So we imagine that the 180-degree pulses are basically instantaneous. We actually tend to operate rather on the edge of that assumption. So there's probably a chance for enterprising graduate students to explore what happens when the pulses really aren't instantaneous in these experiments. So in a single free precession period, of course, the evolution of magnetization is just the solution of the Bloch-McConnell equation. So this is just a restatement of our earlier expression, where now omega contains all the chemical shifts, R contains all of the relaxation rates from processes other than chemical exchange, and K contains all the kinetic rate constants. The effect of the 180-degree pulse is to simply reverse the sign of all the chemical shifts, and that's equivalent to taking the complex conjugate of the evolution matrix. The only imaginary terms in that matrix are the precession frequencies, so inverting the precession frequencies is the same as taking the complex conjugate. And that means we can represent evolution in the CPMG experiment with 3 exponential terms that comprise one CPMG block, in which the middle term, evolution for 2 times tau CP, evolves under a matrix for which we've taken the complex conjugate. That reflects the effect of the 180-degree pulse. And then this whole block will be repeated some number of times to plot out the relaxation decay. You usually start with m equals to 1 and then make it larger, so the overall relaxation time becomes larger. So we have a magnetization decay, and we can define an effective relaxation rate constant, as shown here, in which we have the logarithm of the intensity at some total time t divided by the initial intensity, and then divided by 1 over the total time. So that's just a simple expression assuming a single exponential decay, defining an effective relaxation rate constant. Our interest is in how this relaxation rate constant varies as we vary tau CP. And a graph of the effective relaxation rate constant versus some function of tau CP, and a very common way of plotting is to plot versus 1 over tau CP, is called a relaxation dispersion curve. And our goal is to measure the relaxation dispersion curve and then hopefully extract elements about the matrix L, extract information about the chemical kinetic process. Now, I've depicted this so far as a rather numerical procedure. We measure or calculate the magnetization decay and then calculate an effective relaxation rate constant from the magnetization decay. In fact, there are some theoretical expressions. So for 2-site exchange, one can analytically calculate what the relaxation rate constant is for all time regimes. Those equations are usually called the Carver-Richards equations in the literature, but they're too long to easily fit on the slide, so I haven't typed them out for you. In the Redfield limit, or the fast exchange limit, there are also analytic expressions for more than 2 states, although they haven't been used very much in practice. So here's what dispersion curves look like. This is data from long ago from BPTI. The data points then are the effective rate constants from CPMG experiments with different values of tau CP. The measurements were made at 2 magnetic fields. This turns out, as we'll discuss more in a future lecture, this turns out to be very important in the data analysis that we have data at least 2 magnetic fields. And the solid lines are fits to the Carver-Richards equation for 2-state jumps. And you'll notice that one can have quite peculiar looking relaxation dispersion curves. They're not monotonic. They can have some fine structure in them, particularly as the system moves towards the slow exchange limit. So the goal then is to measure the rate constant, vary tau CP, measure the rate constant again, and then hopefully fit the Carver-Richards equation if it's a 2-state process, or typically these days do a numerical analysis if one has to analyze more than 2 states. So here's some 3-state simulations, for example. This is a linear 3-state system with the indicated parameters. The different graphs show the effect of changing the rate constant for jumps between spin A and spin C. The solid lines are simulations of the rate constant, basically by the procedure that we already described. And the red lines are fitting the 2-state equation to the 3-state dispersion curve. And this is somewhat a bit of warning. You can see that there are regimes in which the 3-state behavior is very similar to the 2-state decay, or in fact the experiments can't distinguish 3-state from 2-state. And then there are, of course, regions that are more favorable where the 2-state model is a very poor fit to the 3-state data. So the warning here, of course, is the mere fact that the 2-state equations fit the data doesn't mean that there's only 2 states. You could simply be in a region of parameter space where the 3-state behavior doesn't deviate very much from some effective 2-state-like behavior. And typically then it's useful, if one can afford the experimental time, to try to change parameters of the system. If data is recorded at a different temperature, if there are 2 jump processes and they have different temperature dependencies, then one might start to separate those processes at one temperature compared to a different temperature. Or you may be able to hypothesize what states you have, perhaps from your biochemical data, and then hopefully use mutations or some other perturbation to shift the relative populations of the states around as a way of trying to convince yourself how many states there really are, or how many detectable states. It's not a simple problem at all. So the CPMG experiments have been extremely popular for applications to proteins and nucleic acids. And there's many, many variants of them, some of which we'll talk about. But they have one drawback, and that is that they use a spin echo. And because the experiment uses a spin echo, one ends up only learning what the absolute value is of the chemical shift difference. So we have a resonance in the NMR spectrum. We're measuring relaxation dispersion on that resonance. We think there's a second state. We analyze the dispersion curve. We get a value of delta omega, but we only know the absolute value. We don't know whether the minor species has a resonance position that's upfield or downfield of the resonance that we see. And one of the major uses of these experiments is to try to learn something structural about the unobservable minor state. We want to do that by estimating structure from the chemical shift, but we then have to know what the chemical shift is. We have to know whether the chemical shift in fact is upfield or downfield. So a drawback to the CPMG experiments is the lack of sensitivity to the absolute sign of the chemical shift difference. There are experiments to help get around that, but it will turn out that the R1 row experiment is naturally sensitive to the sign of the chemical shift difference. And we'll switch to talking now about R1 row experiments, but it's this difference that is making the R1 row experiment increasingly popular, even though technically it's rather more demanding than the CPMG experiments. So just to remind us, R1 row relaxation means relaxation of magnetization that's locked along the direction of the effective field, and we have parameters for the effective field omega e, the tilt angle, etc. Now we can write the same kind of differential equation in the spirit of the Bloch-McConnell equations. It's simply now that instead of having a matrix omega that just contains chemical shift for each species, for each state we have to keep track of all three axes. The shift precession around the z-axis, and then the effects of the omega-1 field that could be on the x-axis or it could be on the y-axis or any axis in between. So if we had two states for transverse magnetization in the absence of a B1 field, our rate matrix had a dimension of 2 by 2. But now for two states, once we turn on the B1 field, our rate matrix is going to be dimension 6 by 6, because the Bloch equation in general is a 3 by 3, and now we're jumping between two states, so we end up with a 6 by 6 matrix. If we have three states, then we'll have a 9 by 9 matrix to deal with. So the major problem in analysis of the R1 row experiment is simply the fact that the matrices become large very quickly. So now, just more or less to repeat what I just said, each site now has three magnetization components along x, y, and z, rather than simply being m plus. Phi here is simply added to indicate that there will be steady state magnetization. The system will evolve to steady state in which there's some magnetization at equilibrium or at steady state projected onto the IZ prime axis. I'm going to ignore this term in the following, but once again, this could be incorporated into an expanded basis of terms in the matrices, and again, I'll refer to Levitt and Gauche as people who have worked in this area. So now to continue introducing the different matrices, we now have a matrix of frequencies for each site. Those are called LA and LB here. A matrix of relaxation rate constants from other relaxation processes, and then the exchange matrix. The exchange matrix needs to be expanded up to be 6 by 6, and that's done by what's called a direct product, which is a standard mathematical approach. So here are what the L matrices look like. We have the frequency, the offset frequency, and the effect of omega-1. I've assumed here that the omega-1 field is along the x-axis, just for convenience. The R matrix for each site has transverse relaxation for the x and y components, and R1 for the z component. And here is the matrix K for two states. If it's expanded up to 6 by 6, it has the following structure. And you can imagine how complicated this starts to get for 9 by 9. So even for 2 spins, the dimensions of the rate matrix are 6 by 6. And in general, there are no analytic solutions in closed form possible. So as an exact solution, there's nothing that can be done other than numerical calculations to whatever precision you regard as necessary. And we can solve this equation, however, using Mathematica, Python, etc., to get numerical results. But we can't get an exact analytic solution the way we could for many of the other problems we've talked about. Of course, if we have to do a very large number of numerical calculations, that could be very useful for analyzing data, but we may end up with tables and tables of numbers that are very hard to get any insight into about the experiment. So we might wonder if there are any analytical approximations that would either be useful for data analysis or give us some insight into the experiment. So once again, R1 rho is the relaxation rate constant for magnetization along the direction of omega e. Now, magnetization orthogonal to that axis decays away rapidly. The relaxation rate constant for magnetization orthogonal to the I prime z axis is called R2 rho, and that tends to be much larger than R1 rho. And in addition, unless we make use of compensated pulse schemes, magnetization that's orthogonal to the spin locking axis will dephase due to B1 inhomogeneity. So we're most interested in the decay along the I prime z axis, and the decay of magnetization components orthogonal to that direction will be much larger. And that means essentially that R1 rho is the negative of the largest eigenvalue. Now the eigenvalues are all negative, so the largest eigenvalue is the eigenvalue closest to 0. So you might think of that as the smallest eigenvalue. It's the smallest eigenvalue in absolute value, but it's negative, so mathematically it's the largest eigenvalue. There's nothing I can do about that confusion. So if we want an approximate expression for R1 rho, then we're reduced to asking, do we have an approximate expression for the least negative eigenvalue of the 6 by 6 matrix, the eigenvalue that's closest to 0? And this turns out to be actually quite simple. The approximate eigenvalue, or a first order approximation to the eigenvalue, is simply the negative of 1 over the trace of the inverse of the matrix, of the Bloch-McConnell matrix. I say that's a simple result. It took us more than a decade of work to realize it. So we had many more complicated schemes, but in the end, it reduces to this simple result. So we take our evolution matrix, calculate its inverse, sum up the diagonal elements, take the reciprocal, and then because that's a negative number, then we just negate it. Now, things can be somewhat simpler. If the relaxation rate constants between the different sites don't differ too much from each other, then this can be the relaxation from the other processes, diffusion type processes, can be treated separately, so we get a projection of the R1s and R2s into the tilted frame, so that the R1 knots and R2 knots can be separated from the exchange contribution. That's then shown here. I'm not going to derive that. We derive that expression, if we wanted to, by a similar procedure that we used in deriving the rotating frame equations at the beginning of this class. And that means then we can approximate the sine squared theta REX part as the negative eigenvalue of simply the L plus K matrix. And that's a little bit of a savings in effort. So that's our first order approximation. Why does this work? Well, the trace of a matrix is the sum of the eigenvalues. The trace of the inverse of a matrix is the sum of the inverse of the eigenvalues. If we want the eigenvalue closest to 0, then its reciprocal is the biggest of all the reciprocals. The other eigenvalues are very large in magnitude, so their reciprocals are very small. So to the extent that the eigenvalues are separated in size, so that the eigenvalue we want is much closer to 0 than all the other eigenvalues, this approximation will work very well. And it turns out that that approximation will be good at least in cases where the populations are skewed. And in many of the applications to proteins or macromolecules, the populations are highly skewed. One has minor site populations of 5% and below when using these experiments. So this turns out to be a quite good approximation. So for the two-state problem, we just simply have to ask Mathematica to calculate the inverse and then form the trace. And here's the result. So the exchange contribution looks similar to our fast limit result, except we have some different frequencies in the denominator. Omega A is the effective frequency using the offset position of the A state. Little omega B is the effective frequency at the offset frequency of the B state. And once again, omega E is the effective field at the average frequency. It's easier to see what this means if we go to the limit where the site populations are highly skewed, say less than 10%. This expression, by the way, was originally derived by Oleg Trott by truncating the characteristic polynomial, a much more complicated procedure where he had to keep track of hundreds of terms. But if the population of B is very small, then omega A and omega E are nearly identical, because the average frequency is very close to the frequency of the A state, so that this combination omega A squared, omega B squared over omega E squared is approximately omega B squared. And if we make that substitution, we see now that R1 rho depends on the offset to the minor state. It actually doesn't depend in this approach on the average resonance position. We did this calculation in the Redfield limit. In the Redfield limit, we found a very similar expression, except we had omega E squared in the denominator. Now we have omega B squared. This says that we can find the minor state, the invisible state's resonance position, by measuring R1 rho while shifting the carrier frequency. And that is a really terrific result. That's what makes R1 rho and the related CEST experiment so powerful and so popular. We can find the chemical shift of the minor state, and then once we know the chemical shift, we can use that as structural information to try to learn something about the structure of the minor state. And this is not predicted, of course, by the fast limit approach. In the fast limit approach, there isn't the minor state frequency. There's only the average frequency in that model. Now, just by way of completion, Baldwin and Kay extended this result to include differences in relaxation rates for the A state and the B state. Their expression is too complicated to fit on the screen. There is a complicated but simpler expression that comes from a perturbation theory treatment of this that shows the effects of differential relaxation rate constants in the A state and the B state. These kinds of expressions turn out to be important for the DEST experiment, where one has exchange between states with very different tumbling times. So we'll come back to this in a future lecture. The main result of this, if we look at this equation for a while, is that the difference in relaxation rates is unimportant whenever K21 is much greater than the absolute difference in the rates. And that means that if the lifetime of the B state is short, then the fact that the B state has a different relaxation rate constant from the A state isn't important. The B state exchanges back to the A state before it can relax in the B state, and therefore we don't care about that. Okay, with that said, that simple trace expression is a first order result. There are standard ways of polishing eigenvalues. So if one just goes to the literature and looks up a standard way of improving an eigenvalue, and we do one cycle of one of these standard algorithms, we can get an expression for a second order approximation to the eigenvalue. And again, if we go to Mathematica and plug numbers in, we then get an expression for the second order approximation to R1 row chemical exchange for two states. It's more complicated expression. It has similar sorts of features as the simpler approximation. More accurate when the B state population becomes larger so that the eigenvalues aren't as separated in magnitude. Again, this was derived in a much more complicated scheme by Vesko-Malushev before we realized that there was this simple trace approach. So here's some numerical calculations. On the left-hand side, the system is near coalescence, exchange broadening. KEX is about 1,000, and the frequency difference is about 1,000, and the B1 field is about 1,000. The upper left panel is a site population of 0.1. The lower left panel increases the site population to 0.25. The black curve is an exact numerical calculation from the 6x6 matrix. The orange curve is the first order approximation, and the blue curve is the second order approximation, which is frequently called the Laguerre approximation based on how it was originally derived. So when the site populations are 0.1, you can see the different approximations agree quite well with the exact numerical calculation. But when the site population increases to 0.25, the first order approximation starts to deviate from the exact numerical calculation. Again, the eigenvalues are starting to approach each other, and the first order approximation isn't as good. Perhaps more interesting is the right-hand side. So the right-hand side, in the upper right, KEX is increased to 2,000. So the system is now starting to be in somewhat faster exchange. Blue and black, you can't even see the black curve, are the exact and the second order approximation. Orange is our fast limit expression from the Redfield equation. The Redfield equation, of course, only has the average frequency. So the parameters were set up so that the population average frequency is 0, and you can see the peak there for the orange curve is at 0. The exact calculation, or our approximation, shows a peak that's non-zero. that peak is at the frequency of the minor state. This is why the experiment is useful. We see that there's a minor state population that's shifted relative to the average peak frequency. And perhaps surprisingly, even if KEX is increased to 5,000, so now KEX is 5 times larger than delta omega, we might think that's actually quite fast exchange. You can see that there's still an offset between the curves. As exchange broadening gets faster, the curves broaden, and eventually we won't be able to tell them apart, and then we really will be in the Redfield limit. But even surprisingly fast exchange still shows the presence of a shift towards the minor state. And al-Hashimi's group in measurements in DNA and RNA have shown that in practice, even for fairly fast limit, that you're still able to distinguish between the offset to the minor state compared to the predictions of Redfield theory. So this property of the R1 row experiment remains useful even into relatively fast exchange, and that was rather unexpected. So here are more graphs. As we said a few minutes ago, the expressions will depend on the difference in the relaxation rate constants from other processes, for processes driven by tumbling. So here are just some sample calculations. So on the left-hand side, the difference in rate constants is relatively small. R2b was given a rate constant of 12 compared to a rate constant of 6 for the A state. And you can see that the different calculations all agree relatively well. On the other hand, if R2b is increased to 200 per second, then the orange curve deviates quite substantially. The orange curve is the approximation derived assuming the rate constants were equal to each other. And of course, this turns out to be a bad assumption when they differ by almost 200 per second. But then on the other hand, either of the formula from Baldwin and Kay or the perturbation treatment that incorporate differences in relaxation rate constants now are quite accurate. So one can handle the situation, the Dest-like situation, where the relaxation rate constants from tumbling are very different, or one could be in the more common limit where those rate constants are relatively simple. Okay, that takes care of 2 states. We might wonder then, what about more than 2 states? And what about systems where we have couplings to take into account? So we can expand all of the above approaches to more than 2 states just by making the matrices bigger. There's nothing really new to be learned fundamentally. So here, for example, would be R1 row for 3 states. And here are some sample calculations for, this actually is 4 states, sample calculations for different geometries for 4 states that are exchanging with each other, and R1 row profiles for different parameters, different field strengths here, and simply to show that the phenomenology can be quite complicated, and there are limits in which one can detect that there are 4 states, because the number of peaks in these relaxation dispersion profiles should be 1 less than the number of states. So the upper row, we can see that there's 3 peaks, suggesting that it's a 4-state system. But then as the parameters change, the peaks start to merge with each other. And you can see in the bottom row, we couldn't distinguish really that there was a 4th state. The system starts to look 3-state-like. So I don't think there's a case in the literature as of yet where a 4-state process has been resolved by these kinds of dispersion experiments without coupling the data to mutagenesis or some other perturbation to, again, try to shift the populations around. But on the other hand, we now have the theory in place as the experiments improve for handling these more complicated systems. Now, for coupled systems, we simply have to replace our column matrices that were the magnetizations with the density operator terms, the operators that would include things like antiphase magnetization that would result from evolution of scalar coupling. So this is quite simple. So here, for example, if we have a 2-state process, but we want to consider what happens to the multiplets, I simply have to have a column vector that includes the appropriate operator terms. And the evolution matrix now has to include the effects of scalar coupling as well as the chemical shifts. So I now have an equation that has larger dimension matrices, but there's not really anything fundamentally different about it compared to the Bloch-McConnell equations. This expanded equation is frequently called the stochastic Liouville equation. And this equation and the Bloch-McConnell equations all depend on a very important assumption, an assumption that I haven't really said anything about until now. And that is that the transition between states doesn't change the element of the density operator that we're concerned with. So in the case of the Bloch-McConnell equations, a jump from state A to state B doesn't change X magnetization into Z magnetization. After the jump, X magnetization is still X magnetization. It just has a new precession frequency or a new relaxation rate constant. Similarly here, a jump of one multiplet component in state A, say the multiplet component whose partner is in the alpha state, if we have a jump to state B, that multiplet component is still in the alpha state. It's not suddenly switched over to the beta state. That's a result of the assumption that the Hamiltonians that we're working with, at least in solution NMR of diamagnetic systems, are too weak to cause a flip of the spins during the actual transition. When we talk about a slow process, a slow kinetic process, what we mean is that the waiting time is long. A molecule in state A is just jostling around in the state A energy basin, and then stochastically has enough energy to jump the barrier. But the jumping of the barrier is fast. The system doesn't slowly ooze over the barrier, at least in the picture that I want to apply here. So if the jumps are fast and the Hamiltonians are weak, then the Hamiltonians can't change the spin state during the transition. And that's a critically important assumption in the Bloch-McConnell equations and in generalizations of the Bloch-McConnell equations to the stochastic Liouville equation. At least in my own experience, I haven't encountered situations where that assumption is violated, but that doesn't mean that there are no cases where that assumption is violated. So it's worth keeping in the back of your mind that everything that I told you about chemical exchange effects in NMR depends on this assumption that the jump doesn't change the spin state, it just changes the evolution matrices from the evolution matrix for state A to that for state B. And with that warning, we finish this lecture.